In this video, we'll discuss the real and distinct eigenvalues case for trying to find general solutions to constant coefficient linear systems. So we know how to find these straight line solutions. They are all of the form v times e to the lambda t for lambda an eigenvalue of the matrix A, and v a corresponding eigenvector. Once we have these solutions, the question always then comes, does this give us a general solution to the entire system x prime equals a times x? And what do we mean by a general solution here? Well, in general, a general solution should be something like a C1 times some solution x1 plus a C2 some solution x2 up to however many of these that I have, so that we can meet every initial condition that we could want to set. In particular, for this, we can look at having each of these be straight line solutions, which would give us a C1 V1 e to the lambda 1t, C2 V2 e to the lambda 2t, and so on up to CK VK e to the lambda kt. And to be even more particular, we can say what happens at t equals 0. Right, we want to be able to meet these initial conditions at any value, but we can just look at t equals 0 to see what that illustrates and see if that gives us an idea going forward. So at t equals 0, this becomes c1 times v1 plus c2 times v2, and so on up to ck times vk. And I want this to be able to meet every initial condition. We've seen these ideas before. This is a linear combination of these eigenvectors. So if I want to meet every initial condition, what does that mean? Well, that means that for every vector x0, which is my initial condition value, I want to be able to find coefficients c1 through ck so that I can take the linear combination of these vectors and I get this vector x0. Now, if we're looking at, say, an n component system for any number n, we'll focus on 2 later. But for any number n, this is going to be some vector in Rn as in an n component vector of real numbers. Now, if I want to be able to do this for every vector, this means I need these linear combinations to cover all of Rn, which really means, in terms of our notation before, I need the span of these vectors v1 up through vk to be all possible n component real number vectors. Now, if I want this to happen in the best way possible, I want them to actually be a basis. I want them to also be linearly independent so I'm not doubling up on any information. So what I really want or need here is that these vectors v1 up through vk form a basis of Rn. They need to be linearly independent because I don't want to double up any solutions here, and they need to span all of Rn, which in particular means that I need k to be n, because all bases have the same number of elements, and I need linear independence. Remember, these v's came from eigenvectors of the matrix A. There's a particular case where we know that a given matrix will have eigenvectors that are real and that are a basis for Rn, and that's if the matrix A has all real and distinct eigenvalues. In the sense that in this case, we know that the eigenvectors that we get form a basis of the entire space, and therefore we can use them to build these solutions. So what does this look like for these particular types of equations? If the matrix A has all real and distinct eigenvalues, and by that I mean that nothing in the characteristic equation has a power that's more than 1, and they're all real, then the general solution to the system x prime equals ax is c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2t all the way up to cn vn e to the lambda n t, where lambda 1 up through lambda n are the eigenvalues of A, and vi for each I is a corresponding eigenvector of lambda I for A. And the idea here is basically that I know that for different eigenvalues, my eigenvectors are linearly independent. And since I have n different eigenvalues, I will get n linearly independent vectors, and so therefore that's from a basis of my space, and therefore this will work for a general solution. We'll be able to meet every initial condition by picking appropriate values of the constants to make this happen. A couple notes from this. So it works for any size system, but we'll be focusing on two components mostly, mainly because we can draw them and understand a little bit better. Also, Obel's theorem that we had from way back when from first order equations also applies here. And what that basically means is that if these solutions are linearly independent at one point, they're independent everywhere. And so I only have to check at t equals 0, which makes all the exponential terms go away. And knowing that they're independent there means they'll be independent everywhere else. And this basically comes back to the fundamental matrix solutions exist. It's invertible, so we're fine. So that's the main idea. If our matrix has real and distinct eigenvalues, it then means we can A, find the eigenvalues, B, find the eigenvectors, and then write the general solution of this form. It's always going to work like this if I have real and distinct eigenvalues. As we go forward, we see a lot of examples of how this works, but the basis is always find the eigenvalues, find the eigenvectors, put them into this form, that gives you a general solution. You can then do whatever you want with it from there.